the symmetry group of a propeller. It will have 3 elements. And as you'll see, I'll have a property that, but I'll draw it so you will understand immediately what it is. Repeat it 3 times, this operation. So now, this is a difficult thing to do. And what you see, it's an object that it has 3 identical parts. So we will call the first one here, we'll call this fundamental domain, where, my convention will be that the first one associated with identity operation. I'll forget the index on it. This one I'll call M2, and this one I'll call M3. So what this group is, it's rotation by 2 pi over 3, and this domain can be rotated here by element 2 and here by element 3. So now the space is covered. This is the top view. Space is covered with 3 copies, 3 blades of a propeller. And the symmetry group is called C3, which is a cyclic group on 3 elements. Now, I can look at this from the side because these things mix up if I'm looking sideways. So from now on, it's going to be your imagination. I'll define a function over this space, and then I will re-express that function in terms of coordinates only in the fundamental domain. So replace the function by 3 functions, which will be vector of dimension 3. Before I had 2. But now, when we look at this, there are several ways at looking at this group. First, we can look at this as an abstract group, without reference to particular physical realization of it, or geometrical realization, or operational realization, if this is combinatorial calculus. So I notice that there is a generator. So I'll call the second element, I'll call it omega. And then I realize that the third element is omega square. Omega cube is identity. Now that will imply that I can think of omega as a cube root of identity. So one natural representation of the group is one-dimensional, but in terms of complex numbers. And this is just e to the 2 pi over 3. So that's one representation. Then the abstract group has a multiplication table. So every group is defined by its multiplication table. First element, second element, and then it's natural to write multiplication tables in terms of inverses on this side. If you do that, then multiplication table has identity on the diagonal. Then elements of the group multiplied by identity. And then it's easy to understand that inverse of rotating twice in one direction is the same as rotating once in the other direction. So just fill it out. So that's a multiplication table for this. Now you can also look at matrix representations. It's a natural way to write multiplication table. Then actually entries in this table are matrices called regular representation of the group, 3 by 3 matrices. So you just read it off from multiplication table. It's inverse of the first element, inverse of the second element. Element first, element second. Element first, element second, inverses. Should be omega squared. So there's something called rearrangement here. Whenever you look at these multiplication tables, they have a property that every row and column has every element in it, and they're just rearranged. So these are 3 possible rearrangements of these 3 elements. So here is one representation. You can actually look at the plane. Again, remember, this space could have 200 dimensions, but we're just looking at it from the top where it rotates nicely, all of its components. But you can think of it as a plane, but it's much more general. In two-dimensional plane, you can write identity to be just unit matrix in the plane. Then you can write element G1 or omega. You can write it as, I won't even, sines and cosines, but just rotation by 2 pi over 3. And omega square, or the second element, is rotation by 2 times. That's an example of matrix representation. Now, in your particular problem, you might be in zillion dimension, and the matrix could be huge. But all it does is it has a property that if you repeat it more than 3 times, you're back to unity.